Now, dear students, now we are going to start the new topic in haloalkanes and haloarenes and the nature of CX bond. Now we will discuss in detail about the nature of CX bond. Nature of CX bond. We know that in haloalkanes and haloarenes, the CX bond is mainly found, and we know that X denotes the halogen elements, halogen atoms, which may be fluorine, chlorine, bromine, iodine, and astatine. But here mainly we consider from fluorine to iodine. We know that in CX type of bond, CX is relatively lower electronegative than halogen atoms, and we also know that from up to down in a periodic table, the atomic size from fluorine to iodine is continuously increased. Like this, the bond length between CX is increased from CF to CI. Okay, the atomic size, it happens because of the due to the difference between the atomic size of fluorine and iodine. Fluorine is the smallest halogen atom and the iodine is the largest halogen atom. So, due to the non-effective overlapping between the atomic orbitals of carbon and fluorine, the bond length differs to each other. But due to the polarization nature, which generally creates due to the difference in electronegativity, the CX bond after the polarization splits into two types of ions, C plus and H minus. After the polarization, due to the less electronegativity to carbon atoms, it bears partially positive charge and halogen atom bears partially negative charge. Here, mainly two concepts are associated with the polarization with the electronegativity of X and C. First, bond length, bond length in CX bond. Number two, bond dissociation enthalpy, which is generally considered in closure per mole. Bond dissociation enthalpy. Bond dissociation enthalpy. Generally, it is considered by the unit of kilojoule per mole. And third is polarization. That means a magnetic properties or considerable properties, which is dipole moment. Right? We know that due to the difference in bond length from CF to CF to CI, we know that the atomic size from chlorine to iodine is continuously increased. So the bond length will be continuously increased from CF to CI. Right? Second concept is that the bond dissociation enthalpy is directly associated with bond length, and we know that due to ineffective overlapping between the atomic orbitals of iodine and carbon atoms, the bond dissociation enthalpy is continuously decreased. Bond dissociation enthalpy, bond dissociation enthalpy is continuously decreased from CF to CI. So we can say that the bond dissociation enthalpy of C of bond is maximum in haloalkanes CI. But when we consider the dipole moment, we know that on increasing the electronegativity of halogen atom, the dipole moment is increased. We can say that the order of dipole moment should be in following order. The order of dipole moment should be in following order. Right? See, order of dipole moment, order of dipole moment, order of dipole moment, which is denoted by mu, and it is measured in by CF, CCl, CBr and CI. But generally it is considered that due to the smallest size of fluorine atom and due to the smallest size of carbon atom, there is much effective the inter-electronic repulsion between the electron density of atomic orbitals of fluorine and the atomic orbitals of carbon. Due to this inter-electronic repulsion, the order of dipole moment is some relatively changed. Then we can say that this is not proper order of dipole moment. Now it can be changed as the proper order of dipole moment will be CCl. After HCl, CBr and CI. Because CCl has maximum dipole moment order than Cl due to the less effective inter-electronic repulsion between the electron density of chlorine atoms and fluorine atoms. Right? तो जनरली ये कुछ कॉन्सेप्ट्स हैं जिनके बारे में हमने पढ़ा है कि एक CX बॉन्ड का नेचर क्या है, इलेक्ट्रोनेगेटिविटी के कारण से CF बॉन्ड या CX बॉन्ड की बॉन्ड लेंथ, बॉन्ड डिसोसिएशन एंथैल्पी एंड द डाइपोल मोमेंट और पोलराइजेशन नेचर किस टाइप से इफेक्ट होता है. ओके, नाउ द नेक्स्ट पॉइंट we will discuss about the formation, we will discuss about the method of formation of haloalkanes. Method of formation of haloalkanes. Method of formation of haloalkanes and arenes, haloalkanes. First is from alcohols. From alcohols. Right? For example, generally we consider the formula of alcohol like this. In this formula, R is alkyl group and OH is alcoholic group, hydroxy group. When the alcohol is treated with halogen acid, when the alcohol is treated with halogen acid into the presence of strong Lewis acid and a strong catalyst, for example ZnCl2, then we obtain haloalkane. Yes. Number 2, when alcohol is treated with sodium bromide into the presence of acidic medium, then we obtain bromoalkane, RPR plus salt, sodium hydrogen sulfate plus water. In the third case, when alcohol is directly halogenated, when alcohol is directly halogenated, then Cl2, when alcohol is directly halogenated into the presence of phosphorus trichloride, then we obtain the haloalkane and chloroalkane plus phosphorus acid. Like this, when alcohol is halogenated into the presence of phosphorus pentachloride, into the presence of red phosphorus, then we obtain haloalkane plus phosphonyl chloride plus HCl. And into the fourth example, we can obtain the haloalkane, which is the most important reaction. When alcohol is treated with thionyl chloride, When the alcohol is treated with thionyl chloride, then we obtain the haloalkane in largest amount. Because in this reaction, the formed two products are escapable gases. So the obtaining total amount, the obtaining total volume of the alcohol will be 100%. There will be no mixture. But in above examples, we cannot obtain the 100% volume of alcohol. There are some mixtures of other byproducts like this: RCl plus SO2 plus HCl. We know that in this reaction, sulfur dioxide and hydrochloric acid, which is already in gaseous, these byproducts are escapable gases in nature. So, due to the lower density, these gases can easily escapable, and the total volume in the container will be obtained by haloalkanes. Okay? Now, generally एक note जो अपन पढ़ रहे हैं, migration to wood, we cannot easily obtain the aryl halide. We cannot easily obtain aryl halide from phenol or aromatic alcohol. Why? We cannot easily obtain aryl halide from phenol and aromatic alcohol. Simplest reason, because in aromatic alcohol or phenol, due to the resonance nature, the C and OH bonds, partially attains the positive charge. Which is difficult than CX bond in haloalkanes or aliphatic haloalkanes. Due to this difficulty, which is just created a double bond nature between the OH and C in aromatic alcohol, it is very difficult to break this bond. So, the substitution reaction and the removal of hydroxyl group from this aromatic alcohol will be difficult. So, easily we can say that we cannot easily obtain the aryl halide in normal conditions because it is very difficult to break this type of bond than CH bond in haloalkanes. One second note, first note and second note. The reactivity order of alcohols towards halogen acids or halogens will be the reactivity order of alkanes, reactivity order of alcohol towards halogen and halogen acid. Halogen acid is 3-degree alcohol, 2-degree alcohol and 1-degree alcohol. We know that when the 1-degree alcohol is treated with halogen acid or halogen, so we require the presence of hard acids, the presence of Lewis acid and catalyst. But when the 3-degree alcohol is treated with halogen acid or halogen, then this type of reaction is generally carried out at the room temperature because the 3-degree alcohol is relatively high reactive than remaining two others. Okay, the reactivity order, mind it. Yes, the first topic, how can we obtain the how can we obtain the haloalkanes? So we can obtain the haloalkanes by the reaction of alcohols. And second method from hydrocarbons. from hydrocarbons. There are so many ways to obtain the haloalkane or haloarenes by hydrocarbons, by radical substitution reactions, by electrophilic substitution reactions, by Markovnikov reactions, by Finkelstein reactions. There are so many ways. First, from, from photochemical, from photochemical substitution, from photochemical substitution of alkane, CS3, CS2. We take an simple example of anulane. When the substitution reaction is made into the presence of UV light and the photochemical light, then we obtain the mixture of primary and secondary haloalkanes. For example, CS3, CS2, 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 Cl plus CS2, CS2, Cl plus CS3. Generally, this reaction is proceeded by free radical substitution reactions. 1 chlorobutane, and second chlorobutane, 2 chlorobutane. This happens practically by free radical substitution reaction, and second one is from electrophilic substitution reaction. From electrophilic substitution reaction, generally we take an example of toluene. We have to obtain the halogen derivative of aliphatic compound or aromatic compound. Then when it is reacted with halogen into the presence of Lewis acid, then we obtain the ortho and para isomer of the compound CS3, X and CS3, ortho isomer and para isomer. Ortho isomer and para isomer. But generally we face a problem in these reactions. When the toluene is reacted with halogen into the presence of Lewis acid, and the formation of product can be obtained by this method, electrophilic substitution reaction. But in the solution mixture, from the solution mixture, how can we obtain the separately this isomer and this isomer, ortho isomer and para isomer? A simplest concept is that the ortho isomer and para isomer can be easily obtained because there is much more difference into the melting point of ortho isomer and para isomers, because generally the para isomers have the most melting point, but the ortho isomer has the less melting point because it is just associated due to the intermolecular hydrogen bonding, which is more than the ortho isomer, right? And generally into the case of iodine, when toluene is reacted with iodine into the presence of Lewis acid, and extra some drops of iodic acid or nitric acid is added, because into the presence of iodine we obtain the mixture of para isomer and HF. When we do not add the nitric acid into the solution mixture, the reaction is reversible. The reaction is reversible if nitric acid is not added, and due to the reversible reaction, we cannot obtain the proper or sufficient amount of the desired product. So, to obtain the desired product, we add some drops of nitric acid, because nitric acid is a strong oxidizing agent which easily oxidized, the hydroiodic acid into iodine, which easily oxidize the hydroiodic acid into iodine, that carry forward the reaction into the desired product. Okay, mind it. When the reaction is carried out into the presence of iodine, then it is compulsory to add some drops of iodine acid, some drops of nitric acid, so that due to the strong oxidizing nature of nitric acid, it oxidizes the hydrogen iodide into the iodine. Right? And third, is by Sandmeyer reaction. By Sandmeyer reaction, very important reaction. This is classified in hydrocarbons, from hydrocarbons. So how can you obtain the haloalkanes or haloarenes from hydrocarbons? Right? From the halogenation or free radical substitution of hydrocarbon, from electrophilic substitution reaction, and third one is from Sandmeyer reaction. From Sandmeyer reaction. What is Sandmeyer reaction? When the primary aromatic amine is just treated with mineral acid like sodium nitrite plus HCl, then we obtain a salt named as diazonium salt. We obtain a salt, diazonium salt, and in further steps, when diazonium salt is treated with, when diazonium salt is treated with cuprous halide, then we obtain the aromatic haloalkane, benzyl halide plus N2 plus C2H. Okay? So we can say that from Sandmeyer reaction we can obtain the haloarenes. But into the case of iodine, we do not react the cuprous halide salt with benzene diazonium salt. But into this case, when we directly add potassium iodide without cuprous halide, then we directly obtain the iodobenzene plus N2 plus K. So these are some selected methods to obtain the haloalkanes and haloarenes from the hydrocarbon. And for example, from alkenes, simple, when ethene is treated with Br2 into the presence of carbon tetrachloride. This type of reaction we have already discussed into analytic chemistry, into practical chemistry in 11th class, and this is mainly used to identification for the detection of presence of double bond in a organic compound. And this compound is CH2Br. Simple thing, vicinal dihalide, 1,2-dibromoethane, right? This third one is CH double bond CH 2 and 1, 2, 4 simple here. When we add it to H here, then this reaction takes place via the path of Markovnikov path. And we know that in Markovnikov rules, the positive part of the reactants always acts at their double bonded carbon atom which already exists, which already contains more number of hydrogen atoms. But the negative part of the reagent is always acts at that carbon atom, at that double bonded carbon atom which is already attached with less number of hydrogen atoms. Right? Now, the desired product we obtain Cl and BrCH3. Right? Now the one question for you. Solve it. The concept you have to apply the concept which I used in above questions. CH double bond CH double bond CH2. You have to find out the desired product. Right? So these are the main concepts to find out, to obtain the desired haloalkanes and haloalkanes from the saturated hydrocarbons. And last reactions from Finkelstein reaction. And we know that the Finkelstein reaction is just an example of halogen exchange. And mainly we obtain the iodo complex. Yes, CH3, CH2, CH2F. Sorry, Br. When this type of bromo compound is treated with sodium iodide in the presence of acetone, this is a characteristic reaction in which always iodo type of haloalkanes are obtained. Here, CH3, CH2, CH2I plus NaBr. You have to consider that in the reactant, bromine atom is attached to first carbon, and the desired product iodine atom is attached with the first carbon atom. So we can say that this is just an example of halogen exchange reaction. And the halogen exchange reaction is known as Finkelstein reaction. And the Finkelstein reaction is a characteristic reaction which is mainly obtained to obtain the desired iodopropane, the iodoalkanes, right? And third is Schwarz reaction. Generally, this reaction is not used to obtain the fluorocomplex because in fluorocomplex, due to the most reactive fluorine atoms, these reactions may be high exothermic and may be hazardous to the students in the lab. Now, in the fourth example, Schwarz reaction. Schwarz reaction. This is also a characteristic reaction, like the Finkelstein reaction. This is also a characteristic reaction in which we obtain mainly fluorocomplex, right? For example, CH3, CH2, CH2I. One iodo-propane. And when this reactant is treated with silver fluoride, diantimonium fluoride, then we mainly obtain the fluorocomplex. We mainly obtain the fluoroalkanes CH3, CH2, CH2F. We know that. How can we say that this is a characteristic reaction to obtain the fluoroalkane? As we have obtained the iodoalkane in Finkelstein reaction, like this we have to obtain the fluoroalkane into the Schwarz reactions, and Schwarz reaction is mainly used for obtaining the fluorocomplex. This is Schwarz reaction. We cannot easily obtain the other haloalkanes like bromopropane, like haloalkanes and like iodoalkanes in this reaction. Okay, dear friends, so now in today's lecture, we have discussed about the nature of sex bond, how can we obtain the haloalkanes and haloarenes from the hydrocarbon and from alcohol, and what are the characteristic reactions of haloalkanes and haloarenes, what are the Schwarz reactions, what are the Winkelstein reactions. It is generally consideration. You have to now solve your problems from the NCERT books, and in next lecture we will discuss about it in detail. Thank you.